I want to guide you through three different examples for signal processing and calculate for the energy. I want to show you the intuitive way. First of all, we have to stick in mind that we have to use some kind of standard formula, and this is the standard formula for the energy. The energy is equal to the integral between minus t and t of x squared of t dt. Maybe it doesn't look really intuitive at first glance, but yeah, now we're gonna look at it. We saw for the first exercise, that probably is the most trivial one. If we give a look to this rectangle at the one, we can say that the t or the x-axis or the t-axis, how you want to call, is between 0 and 6, and that will be our t. And if you look back in the equation, you can see that our t and minus t is going to correspond to the length of where this signal is happening, where this signal has an amount, or whatever amount of amplitude or voltage, and the amplitude in this case indicated as x of t exactly going to be what we put inside over here. What we put inside x squared of t, yeah, it's going to be, sorry, that's a mistake I just wrote. I'm looking out. Actually, the square is going to go outside if we stick with the, yeah, oops. What's going on here? Okay. All right, yes. Okay, let's try to do that. All right, so let's draw again to make it a bit easier to, at this point, between 0, 1, 2, 3, 4, 5, 6, 1, 2. And this is our signal. We need to find the area of the signal. Let's label it x of t, and here we have t. All right. Okay. Therefore, for finding the energy, we want to take the integral between minus t and t. Okay, therefore our minus t and our t is going to be between 0 and 6 of our x of t squared, oops, of dt. All right. Now it could be pretty difficult, but if you look carefully, we are going to integrate on t, and x at this point is going to be a constant. So we just take it out, and we're going to have our x squared, all right? And let's remove the integral because it's going to be pretty much easier to solve. And we're going to stick only with dt. dt is going to be the only terms remaining inside the integral, and we know that we took already calculus in the first, second semesters. If we take the integral of dt, that is the derivative of t, it's going to be simple t, right? Okay, therefore x squared, x is going to be about, I mean, x of t, let's write for make it easy to understand, is going to be about our amplitude, and we know that here our amplitude is going to be equal to 2, because it's actually this length, right? And we're going to multiply between 6, I mean minus 0, therefore, oh sorry, it's squared, yeah, it's squared. Okay, therefore it's going to be 4, then multiply with 6, and our result is going to be 24 joule. Okay, let's go with the other one, a bit less trivial. So we draw again to make it easy to understand. What's going on here? Okay, it's good. Okay, we have our triangle 1, 2, 3, 4. It's between 1 and 4. 1 and 2. We want to find the signal energy 2, and here is 4, this is 1, of this shape. Again, let's always label everything, so never gonna forget. we look back. Okay, yes. And again, now this is a triangle. Probably you already did in statics, so kind of mechanical. Like when there is a triangle, you always divide by 3. I'm not quite sure why the reason. I'm not such a good student, but yeah, I just stick with the reality. You know, like some already calculated difficult reasons, and we can just perform, right? So it's gonna be again the integral between minus t and t of x of t squared, everything divide by 3, and again it's pretty much the same, right? We take x of t squared divided by 3 outside, dt I forgot, yeah, and so therefore again x of t is equal to, so it's gonna be 2 squared divided by 3 of between the area of minus t and t is going to be 1 and 4, right? So between 1 and 4 of dt again is going to be t. Yeah. Therefore, we calculate 4 divided by 3 multiply by 3. We cancel out 3 and our signal energy is going to be equal to 4 joule. Yep. All right. Now we can go to the less trivial part. Oops. That the question was, how much is the energy of x1 multiplied by x2 if this one, let me go back, if this one is considered as x1 and this one is considered as x2, we need to find the signal energy. Again, it's pretty much the same. What the mistake I did, now I'm gonna to draw again and show you what took me so much to understand what I mistake. 1 2 3 4 5 6 1 2, right? Yeah. Yeah, it's pretty bad, but it's pretty all right. T again, next one. 1 2 3 4 1 2. Yeah, that's yeah, not really stick with reality, but you know, sorry guys, could do better, but yeah, too late. All right, if you want to consider about the multiplication, if you look closely, this is something that really make a mistake, but you see that this part here is equal to 0, and if you multiply 0 by whatever number, it's gonna be 0. Therefore, when we take the area during the integral, it's gonna be between 1 and 4, because it is the only part where both have a number, a significant amount, an amount that is more than 0 to find to multiply by each other and don't be a final 0 number, right? Okay, so therefore we still stick with the same thing, right? We have x1 by x2 squared, and we divide by 3 dt. It's going to be pretty much the same. We divide by 3 because there is a triangle, right? There is a rectangle and a triangle. This is like algebra, right? Some algebra that, yeah, probably I even miss myself, but still, all right. Yeah, that's pretty weird, but okay. Therefore, we can go forward with that, and we have 2x1, x2, both amplitude were 2, right? So we have 4 squared. We have actually 4 squared, that's going to be equal to 4 squared divided by 3, and it's going to multiply, if we look, 4 minus 1, right? So the reference is going to be 4 squared divided by 3 multiplied by 3. 3 cancel out. 4 squared is equal to 16 joule. Wow. That's pretty much the final solution. And yeah, that was pretty much. I thank you for your time, and have a nice day.